Okay, good morning, everyone, and welcome to everyone who's joining us for the recording and everyone who's joining us here for the meeting. So our theme today is section 1.4.3 of the lecture notes, which is the technique of integration by parts, which is the last sort of distinct technique of integration that we'll look at in this course. Before that, I'd just like to revisit our topic from yesterday, which was integration by parts. Sorry, I think today is partial fraction expansions. Just one final example on integration by parts before we look at that. This is one that was really belonged with yesterday's topic. But just to recall that and make sure that we have a clear understanding of how the integration by parts technique works, here's one more example on that one. And the example is, this is another sort of classic one that's in every textbook on this topic and every lecture course on it. So that's another reason for mentioning it. So the problem here is to integrate e to the x cosine x. And I suppose glancing at that, our sort of general goal is to try to reach a stage of proficiency where we can sort of glance at a problem like this and figure out what technique might be appropriate for it. We saw yesterday that the technique of integration by parts applies to expressions that you can write as the product of two factors, where one is given the name u, the other is given the name v dash, and essentially the integration by parts formula allows us to rewrite the integral of uv dash as the product uv minus the integral of u dash v. So the goal in applying it is to try to organize your problem so that you can write your integrand as the product of two factors, one of which is called u and the other of which is called v dash, in such a way that you can easily write down the derivative of u, which will be u dash, it appears over here, and that you can easily write down an antiderivative for v dash, which would be called v, and it appears also over here, and also in such a way that hopefully the integral of u dash v is an easier prospect than the integral of u v dash, which is the problem that you would have started with. Okay, so that's a sort of abstract description of how it works. Probably it's easier to follow by looking at how it applies to a particular example. This example, e to the x cosine x, is kind of a classic one. And we'll see the reason for that in a second. The reason, or at least looking at it, I mean, we might observe that it's not really a candidate for a substitution. It has two factors, e to the x and cosine x, but neither of them at all resembles the derivative of the other one. So it doesn't really have the ingredients that would lend itself to a successful substitution approach. It does look potentially like a candidate for integration by parts. It has two factors, e to the x and cosine x, and both of them are things that are kind of manageable from the point of view of taking derivatives and antiderivatives. So the suggestion is throw it into the integration by parts formula, see what comes out, and hope for a successful outcome, basically. So if we do that, and in this particular instance, it doesn't really matter which of these two things we call u and which we call v dash, as we'll see, but let's go with this. Let's put u equal to e to the x and v dash equal to cosine x. Okay, those are the two factors in our problem. To apply the integration by parts technique, we need to write down u dash, but that's an easy job in this case. U is e to the x, so its derivative with respect to x is just e to the x as well. Okay, this is something that we can already sort of note with interest. Maybe, generally with integration by parts problems, you kind of hope that the u factor is going to be something that somehow gets more manageable when you differentiate it. This one is something that stays exactly the same when you differentiate it. So, I mean, at least it doesn't get any worse, but it doesn't really get any better either. So let's see. And then v dash is cosine x. So v will be an antiderivative for that. And the obvious one there is sine x. So fine, again, and v is not much different from v dash in terms of its kind of manageability in terms of calculus. It's sine instead of cosine, but they're very similar functions, as we know. Okay, well, let's throw it all into the formula anyway and see what we get. So doing this, we get integral of e to the x cosine x dx. This bit is u, this bit is v dash. That should be equal to uv minus integral of u dash v. So let's put in all those elements and see what it looks like. Okay, so u is e to the x, v is sine x. So this is e to the x sine x. And then we have minus the integral of u dash v, which is e to the x sine x. Okay, so that's certainly a restatement of our problem. It doesn't look a whole lot better because what we've essentially done is swapped the problem of integration e to the x cosine x for the problem of integration e to the x sine x, which is really very similar, not any harder, unlikely to be any easier. And at this point, it's kind of probably Well, my first reaction probably would be to say, well, this is no better than what I started with, so I need some other idea. This is not going to get me anywhere. I can swap the problem of e to the x cosine x with the completely, similar problem of e to the x sine x, but it doesn't appear to be helping me to solve either one of them, which I think would be a sort of reasonable interpretation of what's happened so far in this example. There's not a strong, compelling reason to persist any further for this approach, but kind of surprisingly, in my opinion at least, there is a value in persisting a bit further. So if we look now at this version of the problem, which is sort of where we are, the e to the x sine x part, in case you're wondering about that, that's fine. I mean, we don't have to do anything with it. So it's part of the solution here, but we don't have to worry about it in the sense that it doesn't have to be integrated or anything. But now if we look at the problem of integrating e to the x sine x dx. Okay, what can we do with that? Well, again, we're kind of in the same boat as we were at the start, not an awful lot. But we can throw it into the integration by parts formula again, for the lack of any other opportunities to do with it. And if we do that, surprisingly, something does actually come out of it. I still find this surprising after all these years of looking at it intermittently. So if you use integration by parts again on that one, again, taking u to be e to the x. So this is not the same u and v as the first round. This refers only to this particular problem. So u is e to the x, u dash is e to the x, v dash is sine x, and v then should be an antiderivative for that, which would be minus cosine x. That's something whose derivative is sine x. Okay, and then sure, yeah, we can plug it all in again and get an expression for this thing that's circled in red there. Will it do anything more than return us to where we started? Let's find out. Okay, so integration by parts applied to that would say that e to the x sine x dx, integral of that thing, should be uv, which would be e to the x times minus cosine x. So minus e to the x cosine x minus integral of u dash v, which is minus integral of e to the x times minus cosine x. So the product of the two minuses there gives us a plus, and we get plus integral of e to the x cosine x dx. So, not at all surprisingly, this has sort of spat back at us the integral that we started with, the problem that we started with, integrate e to the x cosine x dx. And so, it doesn't really look like this is going anywhere, at least not to me. But let's write down everything that we have now and see what it all amounts to. Okay, so fine, that's the integration by parts. This is the uv, and this is the integral of u dash v. Okay, so going back up to this line that's written in green up there, what do we have altogether at this point? We have the statement that the integral of e to the x cosine x dx is equal to e to the x sine x, that's from the green line, minus this stuff. Okay, so minus that stuff is plus e to the x cosine x minus integral of e to the x cosine x dx. And so if we stare at this pink equation for a minute, we can observe that we've got the integral of e to the x cosine x dx on both sides of it, and they don't actually cancel each other. They appear on the two sides with opposite signs, and then we've got some other stuff. So let's just gather it so that the two appearances of the integral there are on the same side of the equation. This is saying that 2 times integral of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x. We better put in a constant of integration at some stage, because we're looking at an indefinite integral. And so remarkably, even though I think this is kind of a weird example, because it sort of feels like we haven't really calculated an integral. We've kind of thrown everything into the integration by parts formula twice, and what has come out is this equation, which actually does tell us that the integral of e to the x cosine x dx is equal to 1/2 e to the x sine x plus e to the x cosine x plus constant of integration, which is an answer. And of course, you can easily check by applying the product rule to the right-hand side there that what you have there is indeed the general antiderivative for the expression e to the x cosine x. So it's an example that I just wanted to sort of make sure that we had a chance to mention, because it is a kind of different one. You know, it's sort of somehow an indirect but successful application of the integration by parts formula that takes 2 rounds, but that actually does give us an answer. And I think especially, like, you know, if I was working on this thing and I didn't already sort of know that it was going to work, I think I'd probably give up after the first step, because it just seems like it's going to go around in circles. But maybe it's a good example to illustrate that sometimes things, you know, sometimes things that look like that's happening actually don't turn out that way. So it's one that's maybe worth studying and worth thinking about, because it is a little bit different from other ones. It's the derivative of cosine, not minus sine. It is, yeah. Did I do something wrong? So the derivative of cosine is minus sine. Antiderivative for sine is minus cosine. Is there a negative sign error there somewhere? I think it's okay. Okay, great, thanks. I think it's okay. If you find a sign mistake, definitely do tell me and I'll fix it. But I think it's all right. But yes, the derivative of cosine x is definitely minus sine x. Okay, so that's the integration by parts. I'll throw up a few more examples on the current week's website, just as a few supplementary examples in case somebody finds them useful. The sort of main reaction on the survey to the question of whether the supplementary examples are useful or not was that a lot of people responded that they haven't necessarily used them yet, but sort of like might use them, so they're kind of like the fact that they're there, and that's, I think, sort of the right or a good approach to take to them. So I'll throw up a few supplementary examples. That doesn't mean that I expect you to look at them, but they're there in case you find them useful, either immediately or at some future point later in the course when you're looking back or whatever. So don't feel compelled to watch every video that appears on the website, because I am well aware that you are bombarded with video content to watch and that it's quite exhausting. So, okay, that brings us to our final technique of integration as such. And I guess there are absolutely endless techniques of integration, and you can fill up libraries with books about them, and people have devoted their entire lives to developing them. So we're not going to look at too many of them, but we are going to look at one more, which is the so-called partial fraction expansion. And to be honest, as techniques of integration go, I think the integration by parts and the substitution are the really important ones in the world of calculus. This partial fraction expansion is a kind of algebraic tool that's very useful to have in your sort of repertoire, and that turns up occasionally in other places, not only in the context of integration. So this is sort of where you tend to first see it, but it's a useful thing to be aware of, and sometimes occasionally turns up in different contexts as well. So we'll have a couple of examples. It's, in all honesty, sort of in terms of its role in calculus, probably less important than the other two, but has the feature that it does occasionally turn up outside of calculus as well. So, okay, so the sort of theme here is we're going to be talking about rational functions. And a rational function is a fraction whose numerator and denominator are both polynomials. And we're going to try to develop some strategies for finding antiderivatives for those. And again, I suppose they are very important functions that turn up a lot in calculus, but also in things like, approximation, numerical analysis, because polynomials are very nice things to work with, but they're also extremely useful for approximating functions that are not so nice to work with. So they do have an important role in science and in mathematics. Okay, so we know how to integrate polynomials themselves. So for example, if somebody hits you with a problem like this, 2x squared plus 3x minus 4, and you want to find an antiderivative, it's relatively manageable, because all you have to do is integrate the terms one by one. And because integration behaves well with respect to taking sums of things, it's not really a major problem. Integrate the 2x squared, you get 2 times x cubed over 3. Integrate the 3x, you get 3x squared over 2. Integrate the minus 4, you get minus 4x. So that's sort of okay. We also know that if we want to integrate something like 1 over x, we get log of the absolute value of x. Okay, and actually, let me also mention, while we're on this topic, that if you want to integrate something like 1 over x plus a, where a is a constant, you get log of the absolute value of x plus a. So, things like x, things that differ from x by a constant sort of fit into the same pattern as x itself there. And if you're in any doubt about that, just confirm it either by taking the substitution u equals x plus a, or by just differentiating the right-hand side and confirming that you get that you get 1 over x plus a. Okay, and we also know that if we want to integrate something like 1 over x to the n, that's x to the power minus n. So as long as n is not, as long as n is not 1, then it's just x to the power minus n plus 1 over n minus 1. So this section is about integrating rational functions. Those are some sort of, I suppose, sort of easy examples of rational functions. But generally, a rational function is something which is a fraction where the numerator and denominator are both polynomials. So it could be something like x squared plus 3x plus 4 over x cubed plus 5x or something plus 3 or whatever, where you can't really apply this knowledge sort of directly, and quite often there's not a whole lot you could do with them. But there are some techniques that work some of the time as usual, and one of them is this partial fraction expansion technique. So let me try to say what that is, and then we'll see how it's useful for integration problems. Okay, so let us take ourselves back to whenever we learned to add fractions, and particularly to add fractions involving algebraic symbols. So if you were presented with the task of adding the fractions 2 over x plus 3 and 1 over x plus 4, for instance, what would you do? Well, more than likely you'd take x plus 3 times x plus 4 as a common denominator, and you'd rewrite both of your fractions with that common denominator, and you'd add the numerators, and you get, as it happens, you get 2 times x plus 4 plus 1 times x plus 3, that's 3x plus 11 over this common denominator. And that would absolutely be the appropriate thing to do if you were presented with that task for some reason. Okay, that's fine. The question is, supposing that instead you were presented with the expression, which is sort of the answer to that addition question, 3x plus 11 over x plus 3 times x plus 4, and asked to rewrite it in the form some number over x plus 3 plus some number over x plus 4. How would you do it? Can you always do it? Do you know in advance that it can be done and that you can find these numbers a and b? Okay, so that's essentially what a partial fraction expansion is. So that's one question, like, can you do it? And second question, well, why would you want to do it? And that's a very fair question. And because usually what we kind of are inclined to do when we see a sum of things is to try to sort of add them up and present this sum as a single expression. And we've sort of, I guess, most or all of us have sort of been trained through our education to kind of do that. When you see a list of things to be added together, the tendency is to just add them together. So you have a single expression as opposed to a sum of things. So the second question there is, well, why would you want to do that? Why would you want to take something that's relatively compact and spread it out and rewrite it as a sum of things? And well, one answer to that is that it might be easier if, for example, what you want to do is integrate the expression, because the two terms in this sum, we know how to integrate them. They're basically log x plus 3 and log x plus 4. This expression, we don't really have a scheme for finding an antiderivative for that as it stands. So that's one reason why you might want to do such a thing. And I suppose, what kind of in the background here is the fact that integration behaves well with respect to addition. If you want to integrate a sum of things, you can just integrate them separately and then add up the results. So kind of being able to express something complicated as a sum of things that are not complicated is very useful if what you want to do is find an antiderivative, or indeed a derivative, because the differentiation and integration operators have this nice property that they behave well with respect to sums. They're not all that nice in general, but with respect to sums, they have one nice property. Okay, so that's one answer to why we might want to do such a thing. There are others that, you kind of encounter in various guises in algebra and combinatorics and the different subject areas, kind of a bit randomly. There's not a, there's not a sort of uniform answer to this question, but it is sometimes a useful thing to be able to do. Okay, so please shout if you have a question, or throw it into the chat at any case, at any stage. Otherwise, I'll keep moving. So the partial fraction expansion is the name that's given to the technique of taking an expression like the one on the right here, on the left, and writing it as a sum of fractions which have the separate factors in the denominator as their individual denominators. Okay, so the question here is, can we take 3x plus 11 divided by x plus 3 and x plus 4 and rewrite it as some number a? So this here I want a and b to be constants. Okay, some number over x plus 3 plus some number over x plus 4. Is that always possible? Can we find these a and b? Are they unique, etc.? These are all the sort of questions we can ask. And the answer is, for a case like this, yes. And a key point here, which I'll come back to a little bit later, is the two fractions here, the two factors in the denominator, x plus 3 and x plus 4, are distinct. If it was x plus 3 squared there in the denominator, that would be a bit different, and we'll look at an example like that later. But as long as you have a problem of this type and the factors in the denominator are different linear expressions, so degree 1 expressions involving x, then you'll always be able to solve this problem without too much trouble indeed. So let's see, how would we solve it? Well, if we just imagine that we can satisfy the equation that's written in the top line there, and take the right-hand side of it, bearing in mind that we don't know yet what a and b are, and rewrite the right-hand side as a single fraction with common denominator x plus 3 times x plus 4, and with a numerator which obviously involves a and b, then a over x plus 3 is a times x plus 4 over x plus 3, x plus 4. Similarly for b over x plus 4, we can write that with the denominator x plus 3, x plus 4. Once we've done that, we can add the two together and write the sum in terms of these unknown quantities a and b. So we'd be saying that 3x plus 11 over this denominator should be equal to, when we gather up everything here, we've got x appearing with the coefficient of a plus coefficient of b, and we've got the constant term, which is 4a plus 3b. Okay, so just separating the numerator there into the x part and the constant part, we've got a plus b times x plus 4a plus 3b. And so if these two fractions, and what I mean there is this fraction and this fraction, if they represent the same expression, if they're equal to each other, they have the same denominator. So if they're equal to each other, they must have the same numerator as well, which means that 3x plus 11 should be equal to a plus b times x plus 4a plus 3b. And that should be true for all values of x, which means that the coefficients of x and the constant term should be equal on both sides. So 3 should be equal to a plus b, and 4a plus 3b should be equal to 11. So that's a pair of simultaneous linear equations which we can solve. I mean, if you're just, we might as well do it since we're here. So, the first equation there, we could rewrite as, for example, let's say 3a plus 3b equals 9. Second equation says 4a plus 3b equals 11. So subtracting the first one there from the second one would give us that a equals 2. And then from a plus b equals 3, we'd get that b equals 1. So certainly, that's a pair of linear equations in variables a and b. We can solve it, and we get the solution b equals 1 and a equals 2. So the expression that we started with, we can write as 2 over x plus 3 plus 1 over x plus 4. Okay. We already knew that because we started by going the other direction. But if we didn't already know it, we would have been able to figure it out using this approach. So and that's a partial fraction expansion. So, kind of applying a partial fraction expansion to this rational function, 3x plus 11 over x plus 3 times x plus 4 means exactly that, splitting it up. So it's a sum of fractions involving the various factors of the denominator. Okay, so that's what a partial fraction is, partial fraction expansion is. And obviously that can be more complicated, there can be more factors involved, but the basic approach is the same. The sort of concept is captured by this example. Okay, anyone have a question or comment? I'll just take let's pause for a minute, just to give ourselves a small breather. Okay, if anyone has a comment or a question, please just feel free to put one in the chat at any stage. Okay, so here if we just look at this again and let's go back to this line where we found the equation 3x plus 11 equal to a plus b times x plus 4a plus 3b. So I suppose the most direct thing to do with that is what we did, to split it up and find that what we need to do is solve a pair of linear equations in a and b. Just to remark, there is an alternative method which sometimes works more efficiently, and certainly for this example they're not so different, but for even slightly more complicated examples this one can be far preferable. So just going back to that line in the previous slide, what we needed to do was find values of a and b for which these equations, for which this equation is satisfied for all values of x. And from the situation that we saw that we can split it up into a pair of linear equations, we know that this will generally have solutions, provided that these two factors are different from each other, which is a small technicality. And so once we know that it has solutions, there sometimes is actually an easier way of seeing what the solutions are than by writing down a system of linear equations, which potentially could have quite a few equations in it and going to all the trouble of solving that. Not too bad if you only have 2 of them, but if you have 3 or more, it can be a bit more of a chore. So another approach at this point would be to say, well, if I want values of a and b for which this equation is satisfied regardless of the value of x, then it must be satisfied for any particular value of x. Okay, I want A and B to be identified so that this equation is always true for x being an abstract variable, but also for any particular value of x. So if you want the statement to be true for all x, then in particular, it should be true at my favorite value of x, whatever that is. Let's say this is x equals minus 4. Okay. And the reason for choosing x equals minus 4 is that if we plug x equals minus 4 into this equation involving A and B, then the left-hand side of it evaluates to some number. The term involving A just drops out because we have minus 4 plus 4, which just evaluates to 0. And the term involving B evaluates to something as well. So when we plug x equals minus 4 into this expression that's marked with a star, on the left-hand side, we get minus 12 plus 11, which is minus 1. On the right-hand side, we get A times 0 plus B times minus 4 plus 3. So this is just saying that minus 1 on the left is equal to B times minus 1. So B is equal to 1. So that immediately gives us the value of B without having to bother with writing down a pair of linear equations that solve them simultaneously. And similarly, if we want this equation to be satisfied for all x's, then it should be satisfied when x equals minus 3. The reason being that that will make the x plus 3 term drop out. And that will give us on the left 3 times minus 3 plus 11, which is 2, equal to A times 1 as it happens. When x is minus 3, x plus 4 is 1. So we just find that A equals 2, which indeed agrees with the answer that we got in the first version. But maybe it's just a slightly different way of reaching the same point. So once you know that a solution exists, and sort of the general principles tell you that, then you could find it sometimes more easily by just plugging in a few choice values of x rather than by solving a pair of simultaneous equations. And as I said, for a small example like this, it's much the same. But for slightly more complicated examples, this method can be far more efficient and far preferable and far less subject to the risk of errors as well. So this method is often more efficient for actually finding the values of these coefficients in the partial fraction expansion. And of course, you can satisfy yourself once you've found the answer that it does indeed work for all values of x and not just for minus 4 and minus 3. And of course, indeed, if you prefer to plug in some other values other than minus 4 and minus 3, you can do that. What you'll get would be sort of another system of equations involving A and B. The key is that by these kind of suitable choices, smart choices of values to choose, we can knock out the A or the B from an equation and write down the solutions more efficiently. Okay, that's the partial fraction expansion technique as such. So it's a technique that applies to kind of rational functions generally. It doesn't necessarily only belong to calculus. But since we are supposed to be talking about integration, if you had the problem of integrating this particular rational function, something that you could do with it would be to apply a partial fraction expansion, as we've just calculated, and then you can express it as the sum of integrals of the two terms that appear in the partial fraction expansions. And those two things are relatively easy to integrate. In the first expression there, we just get 2 times the log of the absolute value of x plus 3. The 2 comes from the numerator. And the second one is just log of absolute value of x plus 4. If you want to, of course, you can write this as log of x plus 3 squared, in which case you don't have to bother with the absolute value sign because it's not negative anyway. But it doesn't matter at all to me whether you prefer to leave it in the original form or apply that little step. Okay, so that's how partial fraction expansions are useful, I suppose, in enabling us to write down antiderivatives for rational functions where we can't see immediately what an antiderivative should be. And I guess, I should issue the general caveat that, like all the other techniques that we're looking at, this one is not unlimited in its scope. And, we should bear in mind that the examples that we're seeing here are sort of handpicked because we can do them. And I know that when I first studied integration, I kind of came away from it with the impression that you can find an antiderivative for anything if you just know the right trick or the right technique or the right substitution. And that's far from true. I mean, there are many, many ordinary looking functions that you can write down that you can't find an antiderivative for in terms of, polynomials, trigonometric functions, exponentials, and so on. They just don't have antiderivatives that can be written in terms of those things. And that applies to lots of rational functions. But sometimes you can apply a partial fraction expansion. Of course, that relies on you being able to factorize the denominator into nice factors, which is the first problem. That may not be possible for lots of examples. But so yeah, bear in mind, I guess, when you're studying these techniques, which is very valuable, that the examples that we're applying them to are sort of picked because they do apply to them. Okay. Anybody have a comment or question? Okay, if not, let's have a look at another example. And this one is, again, a typical kind of rational function. As we've got x cubed plus 3x plus 2 over x plus 1. And the thing to observe here, and again, when you're practicing examples like this, this is kind of the first thing to kind of look out for, to check, is that the degree of the numerator here is 3 and the degree of the denominator is 1. The denominator is not a factor of the numerator. If it was, this would just be a polynomial and life would be good. I guess, again, that's a good thing to check for. If you're in luck, it will be, but in this case, it isn't. But if you've got a case where the numerator has higher degree than the denominator, then basically we could do a sort of division on this thing and write it as a polynomial plus a rational function with the same denominator, but where the degree of the numerator is less than that of the denominator, which is just the remainder upon dividing x cubed plus 3x plus 2 over x plus 1. So the first step, I suppose, if we see an example like this, is to rewrite as a polynomial part. The polynomial, remember, means non-negative powers of x, just with the real coefficients. There's no denominator. So this is the polynomial part, plus a sort of remainder over x plus 1. And the remainder will just be a number. That's the remainder upon dividing x cubed plus 3x plus 2 by x plus 1. So that's sort of the thing to do with an example like this. And of course, it's an opportunity to recall our method for doing long division with polynomials. So maybe I'll squeeze it in here to the side of this slide and make a total mess. So the assertion is that when we apply long division to divide x cubed plus 3x plus 2 over x plus 1, we get a quotient of x squared minus x plus 4 plus and a remainder of minus 2. So let's just see if we agree with that. I'll add a new page just to not make a total mess. Okay, so if we want to divide x cubed plus 3x plus 2 by x plus 1, the usual sort of long division setup, which we don't write down so often anymore. And the first step is to say, well, okay, look at the leading term here, it's x cubed. So to get x cubed, I have to multiply x by x squared. So the first term of the quotient would be x squared. Multiply that by x plus 1, we get x cubed plus x squared. Subtract. That'll cancel the x cubed terms by design. We get minus x squared plus 3x plus 2. So now we're dealing with something which is only quadratic instead of cubic, and that's an improvement. So we now divide the x into minus x squared, just looking at the leading terms of the x here and the minus x squared here. We get minus x when we do that. Multiply the minus x through x plus 1. We get minus x squared minus x. Subtract again. The minus x squareds cancel each other. And again, that's by design, not by accident. And then 3x minus minus x will give us 4x plus 2. And then finally divide the x into the x plus 1 into 4x plus 2. Again, only looking at the leading terms. The x divided into the 4x will give us 4. That's the end of, that's as far as this process goes. We get 4 times x plus 1, 4x plus 4. And then we do a final subtraction, cancelling the x's, and we get minus 2, which is the remainder on this division. And so, we can't really go any further with this. We can't divide x plus 1 into minus 2 and get any more terms of a polynomial. So the conclusion is that when we divide x cubed plus 3x plus 2 by x plus 1, we get the quotient x squared minus x plus 4, and we get the remainder 2. So basically, x cubed plus 3x plus 2 divided by x plus 1, that's illegible. Gives us x squared minus x plus 4 as a quotient. We have a remainder of minus 2, so we also have a term minus 2 over x plus 1. Another way to say that, of course, is that the polynomial x cubed plus 3x plus 2 is x squared minus x plus 4 times x plus 1 plus the remainder of minus 2. Okay, so that's where this line up here comes from. Okay, it's just from that long division. And I guess, when you're looking at these examples of the partial fraction expansions, if you haven't recently practiced this long division technique with polynomials, just practice a bit to remind yourself of it. And if you have any difficulty with it, just give me a shout and I can post a few more examples or whatever, or I can meet you for a quick chat about it. Okay, so that's where we are. So then our problem is to integrate something like this, write it in this form, divide the denominator into the numerator, get a polynomial part, and a part coming from a remainder. So this isn't really a partial fraction expansion, I guess. It's more of a, it's just another approach for this situation. Integrating the polynomial part, we've got x squared minus x plus 4. Take an antiderivative for x squared. This is a standard thing, just increase the power by 1, divide by the new power. So we get 1/3 x cubed. For minus x, same thing, increase the power by 1, divide by the new power. So we get minus 1/2 x squared. From 4, we get 4x. And then we get from this part, we've got minus 2 over x plus 1. That just gives us minus 2 times the log of the absolute value of x plus 1, which again, like the last example, you could write as minus log of x plus 1 squared if you wanted to, and plus constant of integration. Okay, so again, it's a rational function, and I guess the rational functions that we have to kind of worry about are ones where the denominator of the degree of the denominator exceeds the degree of the numerator. That's where we need the sort of partial fraction expansion technique. In cases of the other type, like this one, do the long division first to sort of identify the polynomial part that you can work with, and then deal with the remainder part separately. You'll get some kind of logs or whatever if the denominator had degree 1 to begin with. Okay. So yeah, I mean, to be honest, this is kind of a sample of every type of example that's likely to turn up regarding integrals of rational functions. There's one more example that I want to mention, if it's okay, and I know that this is not the most exciting thing to be spectating for, but there aren't too many more to go, which is a slightly different type of example. And so again, we're only going to deal with cases where the denominator is a product of linear factors. And of course, I mean, you might be thinking, and it would be very reasonable, what about all the other rational functions out there where the denominator is some kind of irreducible quadratic or whatever, irreducible cubic, or some polynomial that doesn't have nice factors? And the answer is yeah, we're not dealing with them. They're not easy to deal with. In cases where the denominator is some kind of quadratic expression, you get things like inverse sines and inverse cosines turning up in integrals. We're not really going to look at those, but they're there, and certainly can easily be looked up in the reference books and so on. And so there's loads of other things that we are going to deal with. The things we are going to deal with are basically cases where the denominator is a product of linear factors. Okay, so this example is sort of like the first one, in that the overall degree of the denominator is cubic. There's a square part and a linear part. Of course, another thing I should just mention is, if you're handed an example like this where the denominator isn't already written as a product of factors, the thing to do there is see if you can factorize it and see if you can write it as a product of linear factors and then apply a partial fraction expansion. Here it is already written that way, so that at least is good. Okay, so the denominator here has 3 linear factors. So it's like the first example, which had 2. The difference, though, is that one of those linear factors is repeated. So there's a 2x plus 1 that appears there twice. And that slightly complicates the partial fraction expansion. So if it was 3 different linear factors in the denominator, like, let's say it was x plus 1, 2x plus 1, and x minus 2, we'd do exactly what we did in the first example. We'd write it as a over x plus 1 plus b over 2x plus 1 plus c over x minus 2, and we'd figure out what the a, b, and c should be using the technique that we used in the first one. If there's a repeated factor, though, that doesn't really work. And I guess the reason for that is, if you were to try something like this, x plus 1 over 2x plus 1 squared times x minus 2 equal to a over 2x plus 1 plus b over 2x plus 1 plus c over 2x plus c over x minus 2, which is kind of what you do if there were 3 different factors, then you're sort of in trouble, because when you look at the right-hand side of it, the common denominator there isn't 2x plus 1 squared times x minus 2. It's just 2x plus 1 times x minus 2. So that approach isn't going to work. If the 3 factors were different, that's what you'd do, and it would work. But in the case where you have a repeated factor, you have to do something slightly different. And what the different thing that you have to do. So I suppose the issue here that we can kind of recognize is that the common denominator of that thing on the right wouldn't be the denominator that we want. It would just be 2x plus 1 times x minus 2. So we wouldn't be able to find a solution. Not 2x plus 1 squared times x minus 2. That's a scroll that's absolutely illegible. But hopefully, along with audio, it might make some bit of sense. This example is also discussed in detail in the lecture notes, I should say, with a bit more commentary than what's written here. Okay, so what you do in a case like this, where you have a repeated factor in the denominator, is basically in the partial fraction expansion, you have to include both a term in which the denominator appears once and a term in which it appears twice. Okay, so and this will work. So basically, instead of taking the three linear factors separately, the one that's repeated appears once by itself and a second time squared. If it was there cubed, we'd need a third one for the cube. So the form of the partial fraction expansion here would be a over 2x plus 1, so that repeated factor, but just once, b over 2x plus 1 squared, and c over x minus 2. And with that adjustment, we will be able to find solutions for a, b, and c. So that's just a kind of comment, I suppose, about what to do in this case, where you have a repeated linear factor in the partial fraction expansion. Okay, so that's the strategy. And okay, we don't know yet that it's going to work, but we can try it out. And so when you expand, as we did the first time round, rewrite the right-hand side with the common denominator. The common denominator now is the thing that we want. It would be 2x plus 1 squared times x minus 2. And just sort of stare at the three factors and figure out what you need to add into the numerator in order to make them have that desired denominator. So the first part, the a bit already has a 2x plus 1, so we need to add another 2x plus 1 and an x minus 2. The b part already has the 2x plus 1 squared as its denominator, so we just need to add the x minus 2 factor. The c part already has the x minus 2, so we need to add both of the 2x plus 1 factors there to make them all have the same denominator. And then, as before, we want these two fractions to be equal to each other, or to represent the same algebraic expression, at least in terms of x. They do have the same denominator. So if they're equivalent fractions, then they must have the same numerator as well, which means that x plus 1 must be equal to this thing, the numerator of the right-hand side. Okay, and now this is a case where we could do as we did in the first version of the first example, look at the coefficients of x squared, x, and the constant term separately on the right. That's a quadratic expression. Compare them to the coefficients 0, 1, and 1 of x squared, x, and constant term on the left. Write down three equations in A, B, C, three linear equations, and then we'd be faced with the problem of solving a system of three linear equations in three variables, which is worse than the case where you have only two of them in two variables. And so that's an absolutely perfectly good option. It'll give us an answer, but it might not be it might be more labor intensive than the alternative approach of just plugging in some values for x. Okay, and here, if, for example, we want the right and left-hand sides of this expression to be equal for all values of x. And so a good strategy is to try out a few choice values of x that will make it simple for us. So if we put x equals 2, for instance, and the rationale there is that will make the x minus 2 term drop out. On the left-hand side, we'll get 3, which is 2 plus 1. On the right-hand side, we'll get a times 0 plus b times 0, because putting x equal to 2 makes the x minus 2 terms drop out, plus c times 5 squared. So from that one, we can find out quickly that c is 3 over 25. It's very typical in these problems to find, not particularly nice fractions turning up as the coefficients. The other nice value of x to choose here that kind of makes the 2x plus 1 term drop out is 1/2, x equals minus 1/2, because that makes 2x plus 1 equal to 0. So plugging that in makes the a and the c terms drop out and leaves us only the b term, and tells us that 1/2, which is what we get on the left when we put x equal to minus 1/2, we get minus 1/2 plus 1, which is 1/2, equal to b times minus 1/2 minus 2, which is minus 5 over 2. And that tells us that b is minus 1/5, which is not too bad, I guess. And then, okay, and because there are only two distinct factors, 2x plus 1 and x minus 2, there are only two choices for x that work in this really nice way. But for the third one, we can just put any value of x at all, put your favorite value of x, for example, x equals 0. So this doesn't make any of the three terms fall away, but it does give us another equation in terms of a, b, and c. The left-hand side evaluates to 1, the right-hand side evaluates to this stuff. But now at this stage, we know what c and b are. So we can use this one to find out what a is, and it turns out to be minus 6 over 25. At this point, we have managed to express our original expression as a sum of expressions with these various denominators. And so those things we can integrate. I won't inflict that on you because we've been on the go for 48 minutes. But the integration at that stage really is the sort of relatively easy part. The partial fraction expansion itself, is where all the work is. Okay, so that's our kind of final technique of integration as such, partial fraction expansions. There are a few examples like it in the current homework sheet, and I can put some more. I can throw up a few more if anybody would like to have a few more. There's no problem at all. Okay, that essentially concludes our techniques of integration, but we revisit this next Wednesday, which will be our final lecture in chapter 1. And at that point, we'll look at section 1.5 of the lecture notes, which is about another thing called improper integrals. Slightly different and slightly more, well, not more interesting, but differently interesting, and not involving learning more techniques of integration, but looking at something else that can occur. Okay, I'm going to stop the recording there. With thanks to everybody who joined us for the recording. Have a good weekend, and we will see you next week.